Morning, everybody. Welcome to a new week of environmental geosciences. Sorry that it didn't get started till Wednesday. I apologize again for having to miss class on Monday, but there's just by the time I woke up, there was no way to even get through a lecture, I don't believe. So I apologize again, and we'll get back to our water resource discussion today. Hopefully, everybody's well rested and being patient with the election results here. So I wanted to review some of the key components of the water aquifer discussion from last class. But the key things I wanted to start with again, which I covered on the lecture for Friday, are looking at the fundamentals of how you can evaluate the viability of a subsurface system, as to be an aquifer. To basically, by definition, the definition of aquifer is that you can produce water for human consumption. And the key variables, physical parameters that make an aquifer viable, again, just to reiterate, are things like porosity, which is a function of the void space within a rock, basically the amount of space between the grains. Obviously, the one on the left is a higher porosity than the one on the right. And I've talked about this, but I'll cover it really quickly. It's just some of the factors like grain size. Whereas grains get smaller, so does the porosity. How well sorted, if something's well sorted, mixing up all the different grain sizes, the porosity goes down. Poorly sorted is better. More heterogeneity, kind of like sorting, it reduces the porosity. And the more things get compacted, obviously, the less space is going to be in there. But I won't test you on all those components. I think it's useful to think about them and know them. But what I do want you to remember is that porosity, the amount of pore space in the rock is what determines porosity, and that's how much space can be filled with water, which gives you an idea of how much storativity, or how much water, based on how much space there is, that a rock unit can hold. The other key term we wanted to introduce here with aquifers is permeability. And permeability is how easily water can flow through those pore spaces. The pore spaces can look an awful lot like this, pore spaces around grains, or they can actually be a fracture that forms that breaks the rock open, which I'll talk about more later on. But the key component here is that all those pore spaces are accessible to fluids, and permeability tells you how much restriction to flow there is of that water going through the pore spaces. So in addition to the same factors that controlled porosity, permeability is affected by grain size, sorting, and heterogeneity in the exact same way the porosity is. In general, porosity and permeability are positively correlated, so more porosity equals more permeability. But the other factors that are important to think about with permeability is how well connected those pores are. If you look back here, these spaces are pretty clearly connected together. You can easily envision water flowing through there. Here, in lower porosity rocks, you can imagine it'd be a lot harder for water to flow through the grain spaces, or at least a lot slower for water to flow through the grain spaces and get to a water well or something like that, or to a river where you could collect the water for drinking or other purposes. I won't test you on this either, but the average distance between grains, the most restricted distance between grains, is called the pore throats. And basically those pore throats, how close the area, the water contacts are, or the grain contacts are where water can flow, the pore throats are what we're talking about in terms of connectivity. The more connected, the wider the pore throats, the easier the water will flow, the more permeable it is. The smaller the pore throats, the less likely the pores are to be connected, and less likely water will flow. And of course, the type of rock material actually plays a big role in each of these factors. But things like gravel, if I put a bucket of gravel, sand, silt, and clay and fill them up with water, you would see that gravel would drain a lot faster than the other ones, and certain things like clay would take quite a long time to flow, just because of all these factors going in the direction of reducing the porosity and the permeability. The last component to remember here is the hydraulic gradient. The simplest way I can conceive of to explain this is filling a garden hose with water and tilting one end up. I think we all know if we have the two ends of the garden hose equal, the water will equilibrate in the bottom of the U-shaped hose and stay there. If I increase one, a little bit of water will eventually flow out. As I increase it more and more and more, a lot of water can flow out. And that hydraulic gradient in nature obviously is in a garden hose, but it's more akin to something like topographic relief, an area like a mountainous area that gets water recharging and flow down. The examples of California, like we've talked about earlier in the semester, it can be snowpack melting in high topographic areas flowing down, can create hydraulic gradients. Or quite frankly, it can just be areas that get, on flat plains that get a lot more rain, where water will flow from high areas of recharge to lower areas of recharge. Looking at places like Ohio, not surprisingly, a lot of the ravines and rivers and stuff like that are often low-lying areas of local topographic induced hydrologic gradients. and they sort of self-perpetuate by the fact that the rivers continue to erode away. But in all cases, you need a gradient that can be made by topography, or it can be made by differences in topography, I should say, or it can be made by putting more water in one case or another. And we'll talk a little bit more about the hydration component of it here in alluvial aquifers. So where we left off at the last lecture on Friday was talking about the different types of aquifers. The most important type of aquifer, even though it's not necessarily the optimal type of aquifer for human water consumption, are alluvial aquifers. Alluvial aquifers, as we've talked about, are typically occur in alluvial type rivers. They tend to have very the river channel itself may not be very wide, but the floodplain deposits are often very wide around the alluvial rivers, as we've talked about. And as a result, near this, here is an example of a paleo river channel. You start to see sediments getting deposited from various flood deposits over and over and over again in that area. And those alluvial flood deposits build up and up and up and up. And as a result, you often see in valley bottoms, particularly in the areas near alluvial rivers, where the sediments will build up over a wide expanse and actually can cover a lot of area and function very much as an important aquifer. So these deposits in alluvial aquifers, are all from these alluvial river channels. It can include things like sand, gravel. It can even include clay, for that matter. And they're all usually found along rivers. And important, along existing river channels. The important part of this is that in most cases, the sediments, be it sand, gravel, or clay, are actually only deposited in shallow areas by the river channel itself, by overflow deposits or flood deposits. And because those sediments are not buried very deeply, and usually not really buried at all, except for by minor compaction of the overlying areas. So you can see here, this would obviously compress the stuff that's below it, but not to the same extent as being buried by by mountain building or something like that. Those sediments are often pretty unconfined, unlithified, and as a result, they preserve a lot of pore space, even though if those rocks, particularly if they're clay rich, those sediments, particularly if they're clay rich, and they were actually very deep enough to make rocks, might actually have low porosity. So the key thing here is they're unconfined, they're often open, the pore space is often open for fluid flow. And another important component of alluvial aquifers is the aquifers are often connected to rivers. So there's a source of water migrating through, in either example here. And as a result, that water, it just prefers to go from a high water pressure to low water pressure. So if the river's flowing around and there's empty pore spaces in the grains below it, those pore spaces will invade into those pore spaces. It's called recharge, and as a result, the river itself often recharges the entire alluvial aquifer around the river channel. So we see this river flowing by, we kind of think of it as water flowing, past us, but the reality is within these unconfined, unlithified alluvial aquifer systems, the aquifer sort of becomes saturated with water up until about the level of the river over time. So as a result, when these aquifers are connected to rivers, even streams, it actually comes to a scenario where you see the surface water invade into alluvial aquifers and actually can be major stores of water. I mentioned some solutions a little bit, and we'll talk about this at the end of this series of lectures, either today or on Friday. But this is actually still a major target for water storativity. Areas in California, for example, are trying to direct more water through alluvial aquifers with the hopes of doing what's called managed aquifer recharge, pumping more water through the rivers, allowing that water to invade into the alluvial aquifer, and trying to saturate that. What's called water banking or managed aquifer recharge, where they're trying to put the water away so later, if they need to, they can actually put wells into the alluvial aquifers and pump it out for human consumption pretty rapidly. Of course, the main reason to do this is not just to put water in alluvial aquifers, and not just to do things like prevent subsidence and stuff like that. It's actually to prevent evaporation. Typically, is the main reason people would like to do that, is storing this up in areas where it won't evaporate for long periods of time. This is the other aspect of this, is that these are usually pretty commonly shallow aquifer tables, very close to the surface, and that's usually defined by the height of the river itself. And as a result, in addition to being really important stores of water, alluvial aquifers are also really important for riparian systems, often create wetlands and ecosystems that can have rich biodiversity, can draw down a lot of carbon dioxide and things like that. So they're really beneficial to most ecosystems and to climate and water needs in the areas. Probably the most famous example of alluvial aquifer. It actually makes up most of the subcontinent of India um, in general. Recognizing that about 3 billion people live in the subcontinent of India and Southeast Asia, basically the foothills of the Himalayas, between almost 3 billion people. And the fact that most of the aquifers in those regions are actually alluvial aquifers, sediments coming down from the Himalayas. It's a fact that alluvial aquifers comprise most of the most important aquifers in the world. They certainly are responsible for providing water to most of the world's people. Like we talked about with the river channel here, these can be pretty wide, and in flat-lying areas next to really big topography like the Himalayas, you actually find that most of the area down below is covered by alluvial deposits. As a result, a lot of the rivers that come out of the Himalayas, the Indus, eventually the Ganges and Brahmaputra, they all have major, wide, encompassing alluvial aquifers that can be thick, can be quite thick sediments being deposited. They can be very wide, and as a result, they can store an awful lot of water. So the Indo-Gangetic alluvial aquifer system, which encompasses again most of the subcontinent of India, is itself responsible for providing water to almost 1 billion people. Just to give you some facts on this, it's about 500 kilometers wide. That's about 200 kilometers, 500 kilometers wide, 200 meters thick. That's over 600 feet per perspective, and basically groundwater pumped in this area is about a quarter of the world's total water pumping in the region, with about 15 to 20 million wells and about 500 million people who directly drink groundwater from alluvial aquifers in the Indo-Gangetic alluvial aquifer system. Importantly, and this is a really important for the next stage of lectures we'll talk about water after we get done water supplies, is that the other nominally 500 million people or more are drinking water from one of a series of rivers, such as the Indus, the Ganges, the Brahmaputra rivers. And in general, because of poor sanitation hygiene systems, poor sewer management systems, those waters are some of the most contaminated in the world. In fact, we'll spend a lot of time on that in the next couple of weeks. I won't go into it very much more. But what I bring up here about the alluvial aquifer system, and this is a truism of alluvial aquifers around the world, is there's actually a sort of hidden problem people don't commonly recognize with alluvial aquifers. They may provide water to a lot of people, like they do here in India. Same is true in China, Vietnam, all the other countries as you move along Southeast Asia, Thailand, who get water from the Himalaya highlands. But the issue, even though we are very well aware, and it's very visual to see the contamination in things like in rivers like the Indus, the Ganges and the Brahmaputra in India, there's actually sort of a hidden contamination in most of these alluvial aquifers. If you think about these alluvial aquifers, they are often alluvial, so they're carrying fresh sediments that are recently eroded from rocks. And as a result of that scenario, they never actually, by being deposited in river plains, they never actually got buried. They didn't undergo chemical weathering. They didn't get heated up. They didn't get broken down to their constituent mineral phases. And as a result of that, these minerals, particularly true in the areas near the Himalayas, so all of India, Pakistan, Bangladesh, and all the way around to China with regard to the areas influenced by the Himalaya weathering, or the alluvial deposits are coming from up here in the Himalayas, is that they tend to be the erosion of young volcanic and metamorphic rocks. Those rocks tend to be very high in certain metals, arsenic being one of the most important ones. And as a result, you have a half million people using this aquifer source, and it looks a lot better than water that's directly recovered from some of the key rivers. But those aquifers are actually, the alluvial grains in those aquifers are actually being chemically weathered and broken down now. And as a result, there's a high incidence of arsenic poisoning specifically, which is naturally occurring, has nothing to do with any human activity. It's just simply harvesting water from these young geologically recently deposited sediments that are rich in arsenic. So as a result, you actually see that in that region, there's major incidences of arsenic contamination that occurs naturally. There's a famous paper written about the arsenic in this area, about how Mother Nature gets away with murder because of the number of ill and deceased people that have suffered from arsenic poisoning. We'll talk about geological contamination a bit more in the discussion of water quality next week. But the key thing I want to mention here is that even though alluvial aquifers provide a quarter of the world's water, they actually provide about half of the world's natural groundwater contamination issues, which we'll get into more. The second major form of aquifers are actually what we call sedimentary or hard rock aquifers. These are areas where sediments were deposited and buried deeply enough to become lithified to rocks, sedimentary rocks, or in some cases they can actually have some other metamorphic or igneous rocks in those components, but they typically are sedimentary rocks. More rather than being deposited in a river channel itself, these are sediments that are deposited in marine environments, typically in beach deposits or onto the continental shelf of the shallow ocean. Most of these sediments, just like we see the sedimentary rocks in Ohio, are deposited when you have a major mountain building event. In our case, it's the Appalachian Mountains that eroded and eroded and eroded into deltas and into the marine environments and got deposited as sedimentary rocks. And then over time, those rocks are buried deeply enough to be lithified. So what we're looking at in these sedimentary and hard rock aquifers is actually the fact that the permeable sediment rocks have enough space stored in them. So that's the porosity, and that space is connected enough, i.e. the permeability, to the sandstones or even some carbonates, but typically sandstones, will allow water to flow through them. So the most famous example in the United States is something called the Coconino sandstone. It's actually deposited, this is actually out in Arizona, New Mexico. It's deposited during the uplift of the Rocky Mountains. And as a result, it gets recharged from the Rocky Mountains, and water's flowed through this area for quite a long time. So if you look at things like the Colorado River, a lot of the river discharge in the Colorado comes from water that flows through the Coconino sandstone, for example, and into the rivers in certain locations. Most of the southwestern region of the United States, Arizona, New Mexico, even parts of Southern California, depend greatly upon water pumped from the Coconino sandstone to offset the water they can't get from the Colorado River system. So I won't touch on the sandstone, but this is a major aquifer, particularly in northern Arizona and New Mexico, for providing water to the region where we talked about the water needs related to the Colorado River. This is just a picture of the Coconino sandstone. If you've been to this part of Arizona, you can see pretty readily it's as dry as you can imagine. It's got very little vegetation, very little water, not much going on. But the Coconino sandstone actually provides, if you can drill deeply enough to get to it, provides access to some of the best water in the world, and quite a lot of it, in fact. The third type of aquifers, which are actually very important I should have said this, sandstones. Along with sandstones, there are also important sandstone aquifers in Ohio, but the carbonate aquifers, particularly in the western half of Ohio and into Kentucky and up into Michigan, are really important. And these are called carbonate or karst aquifers. The key thing here is not the amount of pore spaces in the sediments as they're deposited, but typically these are major carbonate rocks. The carbonate rocks are deposited massively, so very large aerial extents and often very thick. And they're typically deposited in sort of shallow marine environments. So not the beach environment, but if you go out a few hundred meters into the beach, off the beach, into the water off the beach, you'll find that carbonate deposition occurs on most of the continental slopes. So for several hundred kilometers out into the oceans. And as a result, you get these big, thick, massive carbonate deposits. They often get placed as part of the sedimentary package. If you go out to the geology, you look at the geology of Ohio, there's carbonate deposits all throughout Ohio, and the subsurface in eastern Ohio and at the surface in western Ohio. What happens over time is water percolates into sort of small fractures that form near the top of rocks, the carbonate rocks. The acidity, natural or induced in rain, actually weathers the carbonates. And as a result, fractures get bigger and bigger and bigger, and eventually those fractures become full-blown caverns or pathways for underground water flow. That porosity, typically caused by fracturing initially, and eventually when it's weathered out, they're called vugs. I won't test you on that, but VUG, vugs, are actually what creates the things like the caverns you see in different parts of the Kentucky and Ohio. So this is a really an important family of aquifers. It can be limestone or dolostone. There are two types of carbonates, but the key aspect here is karst. It's when there's enough space below them that you sort of see caves forming, you see water transmitted really easily through them. You can imagine why carbonates are much more massive than sandstones. They're much more prevalent in the rock record. They're bigger when they occur, and they're much more extensive. So you can imagine if you're in an area and there's a karst aquifer, and you can drill a well into a flowing system like this, you can imagine you can pump water on those for a very long time. So these are incredibly important in regions where you want to have high water usage, such as major urban areas, but particularly for agriculture and industry to have access to karst topographies. These can be complex. You could drill down, here and not hit any of the karsts and actually have really low productivity. So typically you have to drill till you hit one of these. They're not really caverns, and it's not really an underground river, but till you hit one of these vugs that have access to water in them, which kind of uses that fractured and eroded porosity and permeability to get water out. So this term I'm going to introduce here is important as secondary porosity. So this is, as I mentioned, caused by chemical weathering, by acid weathering with carbonate rocks. As a result, it typically started by fractures near the surface, and then by the dissolution of carbonates along those fracture planes and make vugs and eventually can be caverns for that matter. So that's all called secondary porosity. From the aspect of how it was formed, that's important. But in reality, when you're thinking about whether you can get water in or out of those carbonate rocks, we don't really care. And in essence, the key lesson to learn here is that carbonates or karsts, you create a lot of porosity, secondary porosity by chemical weathering, and that makes pumping water from those aquifers all the easier. So as a result, in terms of the scope and scale size of the aquifers, carbonates are probably the second to alluvial aquifers. Not nearly as much water is produced from them, but the key thing is where they are there. They can be really massive producers of water if the aquifer water table is high enough, which in our neck of the woods is exactly what we find. So very, very productive aquifers, and most importantly, very high quality water from them. They tend to be very, good tasting, not a lot of foul smells. They tend to be buffered by calcium carbonate dissolution, so they don't often become acidic or have any enrichments of metals or anything like that. A few examples, not necessarily as an aquifer, but of a result of this secondary porosity formation, are actually the Ohio caverns, which are located just northwest of Columbus. If you look at the Mammoth Caves and the big aspect of Kentucky tourism, and in fact Ohio tourism is based upon this exact calcium carbonate dissolution created by secondary porosity, which actually, as you can see, creates pathways where water can actually flow underground. So it's quite important. If you look at a map of Ohio, the vast majority of the western half of the state of Ohio is actually in a carbonate aquifer, where most of the water that's produced is actually done by drilling municipal wells into or agricultural wells into karstic terrains, where you can access some of those void spaces and pump water. What's funny, if you'll entertain me for a moment, is that the eastern half of Ohio is actually dominantly sandstone and shales. So it really depends on that initial porosity that we talked about, or what we call primary porosity in earth sciences, and it really depends on the amount of space that occurs between the grains where water can flow through. I've done a lot of work on contamination related to hydraulic fracturing, or evaluating where it occurs really in eastern Ohio, and everybody there tells me that their particular farm well was drilled in an area where there's an underground river, and that's why the well was placed there. But in reality, that can be true in western Ohio, and really never is in eastern Ohio. But often you see a lot of drillers and stuff like that love to, good salesmanship in terms of convincing them they found the best spot for them. So, putting this in perspective, how much water in these different types of aquifers is actually going to be available for production? Just to give you a perspective on this, within the contiguous United States, so the 48 lower states, if you look at the water that's accessible within a half mile of the land surface, so that's for perspective, that's more than 2,600 feet, right? So that's deeper than we're probably drilling for water wells, but we certainly drill there for shale gas development, for oil production, and actually oftentimes for brine production to get certain elements from brines. There's between 30,000 and 54,000 cubic miles of water. That's a number that's quite frankly impossible to understand. So I'll give you a equivalent, something that might make a little more sense. If you were to take the amount of water stored in aquifers in the contiguous United States, that's equivalent to the flow of the Mississippi River over the last 200 years. So just think about how much water is going to the Mississippi every single second, and recognize that, on the scale of comparison, the groundwater storativity is much larger than the Mississippi River on a multi-century scale. And that kind of highlights the point I made in the lectures last week, which is that even though about half the water in the United States, actually even more than half the water in the United States utilizes surface water, it actually, is a disproportionately small amount of water in the total volume of water that's available in the regions. So as we've already alluded to in California, unfortunately, the use of this groundwater research, even though it's massively large, and this is not just true in the United States, it's true in a lot of places, is unfortunately much greater than the actual recharge rates to manage the balance between how much an aquifer can store and how much is currently in there. And as a result, you often see that groundwater withdrawal in many regions of the country, California we already talked about, exceeds natural inflow and recharge, in some cases substantially. So just to redefine this, when the withdrawal exceeds natural inflow and recharge, it's called groundwater overdraft or groundwater deficit. Some people call it groundwater drawdown. Any of those terms are fine, and I won't test you on the vocabulary of that or the nuances of the vocabulary of that. But the key thing to recognize here is that in many parts of the United States, the biggest threat to water security comes from the fact that groundwater overdraft has already occurred in that area. So we talked about water security and related to Colorado, and there's major concerns there. Those are clearly impact a lot of people. But if you look at the big picture, how much it would affect local populations, how much it would affect local drinking water supplies, how much it would affect local sanitation hygiene supplies, groundwater overdraft is comparable. What makes a huge difference in terms of things like groundwater overdraft is actually the longer downstream impacts of water loss in those areas. So for example, the vast majority of America's food comes from the Imperial Valley of California and the High Plains Aquifer in the Central Plains region of the country. And both of those places, because of those agricultural activities, have experienced extreme groundwater overdraft, and actually groundwater overdraft in levels that are now in critical stages where, quite frankly, there are many parts of this region in particular where the 20-year forecast does not actually suggest that there's going to be water to pump for any needs in that region. We'll talk about these in specific now for most of the rest of today. But just for perspective, in Ohio, as you see every spring and every fall, our reservoirs go up and down. This year was actually relatively, we went into a modest drought, minor to modest drought this year. If you're looking at some of the reservoirs, the furthest extents of the reservoirs in the areas we've been driving around, maybe with COVID you haven't been able to, or sort of dried up. The reservoirs are still totally, replenished in this region, and the groundwater aquifers went down a little bit, but in reality are perfectly fine. For most of the sort of northeastern Great Lakes region, overdraft's not a concern, and that's because of the fact there's enough rain in those areas that people can disproportionately use the surface water in these areas, or just rely on precipitation for agriculture. Clearly, as you get to other parts of the U.S., in particular the southern Mississippi River Valley, southeastern United States and Florida, and most of the Mountain West, there's moderate overdraft. So basically what that means in those areas is that drawdown is actually occurring faster than replenishment. So the aquifers are dropping year over year, but it hasn't gotten to a critical level yet where there's actual shortfalls on the projected water budgets. This doesn't mean it's not important in these areas. I'm going to give you two examples. In Florida, that moderate drawdown is drawing the water down, and if you watch the news, pick your favorite news channel and watch it. At least once a year, you'll hear about a collapse in ground collapse in Florida, where there's a carbonate subsidence. Usually, what those are actually karsts being formed. So this situation where that karst comes down, this area eventually collapses into that, and those sinkholes become pretty prevalent in areas like Florida. A big part of the reason those sinkholes occur in this region is because the water table has been drawn down. So, it's only a moderate overdraft. There's still enough water. You might not think that's a concern for municipal water supplies, but if you're the homeowner or the landowner where that sinkhole forms, obviously it can be a really devastating scenario. The other important thing with the overdraft it's only moderate in these areas is actually a balance between fresh water and seawater. If you draw down the aquifers near the coastlines, you can actually see what's called saltwater intrusion, where the pore space gets drawn down. That puts more hydraulic head or more pressure of water in the ocean, and that water actually invades the lithologies near the surface, and that can actually cause the water quality to be pretty severely diminished and actually basically become unpotable. So I don't want to mean to say it's not important, but just not as drastic as the areas we're gonna talk about here in a few minutes. The Mississippi River Valley is actually quite interesting in the sense that most of the drawdown in that area is using alluvial aquifers for agriculture, rice fields, a lot of farm fishing uses really copious amounts of water. As what we've seen drawdown, there's two implications here. Some of the major cities like Memphis, along the Mississippi, they experienced local drawdown, and they started to see subsidence in the area. They also started to see salinization of their aquifers, just because saltier water was been in the ground for a long time was now being pumped, and the water quality diminished. In those areas, there have been major projects to try to divert the Mississippi River and use that alluvial recharge to recharge both the aquifers and also prevent further subsidence in the regions. Another concern, although it hasn't really been realized as much as when fracking reintroduced water to the aquifers, is that there's some concern that drawdown in that area. It's a very seismically active area, that there's some potential that drawdown could eventually induce some seismicity, but that's sort of been somewhat unfounded. But most of the coastal part of the Gulf Coast here, because of that, the potential for moderate drawdown still is a concern along the coastline for saltwater intrusion, which again reduces water quality and has pretty lasting implications. Hard to flush that saltwater back out. But where we started with this discussion really was talking about the severe areas, and I'm going to talk a lot about the Great Plains, or the Great Plains region of the U.S., the High Plains Aquifer region, and we've already talked about California before. These are areas where, in your lifetime, we're going to make decisions about if people can continue to live there, if businesses continue to be there, and how we're going to use water that are going to get a lot more serious and much more dire. So before we get into how we came up with these deficits and what they mean, I thought I'd talk a little bit about how we actually get groundwater out of the ground. How does this drawdown occur? The key thing is that most of the water source from the ground is actually removed by a well. We all have these sort of maybe romantic visions of little wishing wells and small wells and farm wells that look like this or have little rocks around them, from years past. In some cases, that's what the wells look like today. If you actually have one of these by you, I encourage you to take a good look at it. It actually is pretty informative about understanding how the subsurface aquifer system looks. If you look down the well, if you drop a stone or a penny down there, you'll eventually hear a splash. At least we sure hope so. And that basically actually tells you the elevation of the water table. That's the depth where the water actually flows to naturally. If you go into a drought, that will go down. If you go into flood, that'll go up. But basically, it tells you where the surface expression of the water is locally. And the typical aspect of the well, a simplistic well, is just digging down till you get to that water table and making sure it's deep enough that it can accommodate those fluctuations. And we can do that by a bunch of different ways we'll talk about here in a minute. In this simple type of example, you're just, you can literally take a bucket on a rope, pull it down, suck up some water. What happens when you do that, and it's true in any type of well, is the water surface will go down temporarily where you move it, and over time it'll re-equilibrate. If there's no new water coming into the system, it'll re-equilibrate across the whole aquifer down a little bit. If there's new water coming in, of course, it'll rise. But basically, over time, there'll be a re-equilibration of that water. What's important here is the different types of wells and what they can do. So there are three main types of wells, all of which are still used today, particularly in the U.S. Certainly in developing nations like in most of those sub-Saharan African countries, a lot of wells are actually hand dug. People are literally, going down and digging wells, or doing it with a jack and a jackhammer, and basically bucketing the materials out. But hand dug wells are still commonly used. Another one is what's called a driven well or a drive point well. If you've ever heard these, they often they're doing this near construction sites on campus a lot now. I don't know if you're on campus or you're hearing this, but they'll hear them bang, bang, bang. They drive an actual steel spike down to the ground, and then they pull the spike back out, and that creates a borehole that can fill with water. And the most common, or at least most sophisticated, best way now is actually what's called a drilled well. It can be done in a few different ways itself, which I won't go into, but it's actually drilling a uniform borehole throughout the entire thing. It's most expensive, but it's actually the most controllable for managing the quality of the well, make sure it doesn't collapse, and make sure we can get exactly where we want to get to. So, key aspects of these dug wells are commonly dug by hand, still dug by hand in many parts of the world. many millions of wells in areas like India and again sub-Saharan Africa, as examples I showed you in the alluvial aquifers there in India, are dug by human hands, that just digging a hole deeper and deeper and deeper. And again, the advantage of these is that they don't really require many resources. You don't need equipment. You don't need motorized vehicles. You can sort of do it by brute strength if you have a pretty accessible picks and shovels and buckets and whatnot. In general, that hand dug wells is usually pretty wide, which is a plus and a minus. We'll come back to in a second. And then usually what's done is it's fortified by lining with stone. Some people actually use cement. They try to preserve that big borehole with some sort of reinforcement like that. The second one, the driven wells, are very common, not so much for municipal wells or major agricultural wells in the United States, but they're commonly done sort of if you have anyone has a little cottage down in Hocking Hills or rural areas like that. These driven wells, like you hear, are going on campus right now for construction, are often used to sort of install pretty low cost wells near a cottage. It's cost a few $1,000s and get a well in. If you don't have a very large water demand, it can usually make up enough water. And then the boreholes are now most common. They're most expensive. You can think anywhere from $10,000 to $50,000 to sink one in, but when you get it in there, if it's built properly, you're probably going to reliably be able to drill to the right depth and get water, for a substantial period of time. Now there's some pluses and minuses. This is actually a well that's on the University of Kentucky's campus near their College of Agriculture. It's an old hand dug well lined by stones here, as you can see. Again, the advantage here is it's hand dug. It's basically built for nothing but human effort. But the disadvantage of these is it taps shallow groundwater. By necessity, people aren't going to be able to dig through a bunch of water. So, I mean, what's the predictable surprise here? If you're tapping a shallow aquifer and you have a drought, the water table can pretty quickly go below the depth at which you can dig to. And additionally, it's very easy for contamination to get there. There's various paths. People can dump stuff into the well. People can, you heard the term poison the well, right? That was a thing people do as a means of warfare or just torment. Also, these shallow aquifers can be influenced, particularly, in areas like Ohio. These hand dug wells are often shallow enough that septic tank leach fields and other forms of contamination, the person dumping gasoline out behind the shed, can often get in here, and many of these shallow systems have been contaminated. But this technology, again, has been around for a long time. This example on the bottom is a 2,000-year-old well at Kafir Kala in Afghanistan. And this is a sort of unimaginable, think about, this is a 200-foot deep hand-dug well that was actually lined by sort of stone, brick, and mortar for most of the well, which was a major water supply in the region. So people are very industrious, dug these for the great depths, for quite a long time. But in general, particularly in industrialized nations where we are using chemicals, where we're seeing various chemicals get into the environment, and most importantly, where we're realizing where populations are increasing, and which is true almost all the world, the bigger issues that shallow wells just aren't feasible for, things like septic leaches, nitrates, phosphate poisoning, stuff like that. So in general, we've moved away from shallow wells anymore. The deeper the well, takes a longer time for the contamination to get there, and as a result, there's less concerns about contamination from surface spills and things like that. More importantly, and this can be true of either the driven or the drilled wells, driven or drilled boreholes, is that in addition to preventing contamination, they're often far more resilient to drought. Being deeper, the water table might go up or down in a given, the rainy season might go up, or certain times of the year, spring rains might go up, summertime or droughts might go down. But if the well's drilled deeply enough, the well will stay within the water table, and you can sort of position the pump in your well to make sure you can harvest water without any risk. So, if you're doing an agricultural well, even a domestic well nowadays, unless you're in a scenario where water poverty and general poverty are a risk, most houses actually have municipal water supplies, or they'll have wells drilled by a borehole or a driven well pretty deeply. Now, in Ohio, an average to think about here, not uncommon at all to see a well at 150 feet or deeper, which is are really responsible for contamination and drought resiliency. Um, but it's also true that you can see them be much deeper. So again, 100 feet, 200 feet, common. I've seen wells 900 feet. In fact, just this summer, we did some sampling. I found I had a sample well that was 980 feet deep in just a bit west of Columbus here. So people can drill deeper to make sure that they're going to always be within the water table. It all comes down to how much cost do you want to put into the upfront investment. So there's no limits on these now. Water wells can be drilled 1,000 feet or more, and that's not uncommon, particularly in southwestern United States to reach that coconina sandstone, for example. They do it, but the reality is that the cost goes up. To give you perspective on this, a good number to keep in your head is basically $100 a foot. That's about how much it costs to get to the depth to drill a well. And as a result, if you're talking a 1,000-foot well, you're talking $100,000 of capital to drill that well itself. So how do we actually drill these wells? This is actually an example from the coconina sandstone. This is a drilled well. This is called a rotary well. Well, it actually has a bit that turns and has teeth on the bit that grind the rock out. So this is a pretty large rig, but here's them actually drilling in Arizona in the coconina sandstone, and you can see here it's a pretty massive operation that very quickly produces quite a lot of water. And if the one thing I'll say here about the deeper wells, it's not just preventing contamination and preventing and being drought resistant. There's also the reality that there's more hydrologic pressure on the wells at deeper. They are deeper, so there's more cost up front. But many of these municipal water wells in Arizona from the coconina produce 2,000 gallons per minute, which is pretty massive. Some of the wells we install in the in Tanzania and the Navajo Nation with the Global Water Institute, produce something like 500 gallons per day. These are 2,000 gallons per minute for perspective. So the other facet here, other than droughts and contamination and depth that you want to consider, is that drawdown is again really important and due to pumping. That's where these overdraws come from, actually seeing drawdown occur. So how does this actually happen? Well, the key thing here is that wells are pumped. As we mentioned, the water level will decline, and what happens is obviously water is going to get pumped into from very close to the well first. This creates what's called a cone depression. That cone depression is initially very small and narrow and keeps getting bigger and bigger and bigger and bigger as the water is drawn down. So it's not that the whole water table just draws down like this. Over time, if it was left to equilibrate, it would. But because we typically pump faster than the water invades, what happens is cone depression forms, gets bigger, deeper, and more and wider over time. So as you can see here, this is just an example from Kansas. An agriculture well in that region can often have an influence that affects the surface water levels over hundreds of meters, for example. Tying this back to things like porosity and permeability, the higher the porosity, the higher the permeability, the more uniform it'll be drawn down quickly, and the more sort of discrete and close to your well the cone depression will be. The lower the porosity, the lower the permeability, the more it's going to be wide and slow and very slow to re-equilibrate. So, particularly in Kansas, you're talking about sort of sandstone aquifers. They have connectivity, but they're not very high permeability. So they have porosity and connectivity, but it's not very high. So relatively modest permeability, and as a result, drawdown can be quite extreme in those cases. In karst aquifers, it might equilibrate much more readily, and in alluvial aquifers. Sorry, I thought I was going to make it through the lecture, but I'm not sure if I'll get all the way to 10:05. In alluvial aquifers, they tend to be very porous, and the level remains pretty flat. So, again, the drawdown is the difference between what's a natural level established by recharge and water used by evapotranspiration and pumping levels. Key thing here is that this can be very modest. It can be less than a foot. It can be hundreds of feet if there's low porosity, low permeability units, or in fact there's just not any recharge coming into the system, which is often the case. So what's the eventuality of drawdowns? Well, for starters, you can pump out all stored water. The water can be lost. The shallow wells, of course, if you have a farm well that maybe it's been here for hundreds of years, a hand dug well producing water, you've been really careful to not allow any contamination. and that farmer next door puts a water well in and starts pumping, or you put your own agricultural well there and start pumping, you can often see the shallow wells will eventually go dry. We mentioned particularly the alluvial aquifers, you often see along river channels in these alluvial aquifer systems, shallow hydration, saturated with hydration. As a result, you see large wetlands or riparian zones, a lot of vegetation in river channels. As that water table gets drawn down, the riparian vegetation can be killed off entirely. We've talked about this in California, but we'll come back to this again. Land subsidence is sort of the next stage. Once this gets drawn down in this area, think about the average sedimentary rock, for example, having about 30% porosity. If you remove the water out of 100 foot of rock entirely, that means over time you could actually expect to see a subsidence of about 30 feet in that area, which is pretty profound. Imagine you're walking out of your house and finding a 30-foot depression next to you. That would be pretty stark. There can be things like natural releases of contaminants. Methane is a common one in our part of the world where there's methane that might have migrated up from Marcellus or something like that naturally. It's in the aquifer system. There's enough water there to hold it in place. If you draw that water down, boom, methane releases. You can see elevated methanes, even explosions in houses. Those can also be caused by other factors, including aspects of drilling we'll talk about in a few lectures. But this has important implications for particularly with land subsidence and loss of vegetation that can have pretty profound effects. So we've already talked about this a little bit in terms of California. I'm going to start talking about it in terms of the High Plains Aquifer case study now. Just to get you familiarized, the High Plains Aquifer starts in southern half of South Dakota, a little bit of Wyoming, and then encompasses almost all of Nebraska, a good amount of Colorado, Kansas, the western panhandle of Oklahoma, and down into North Texas here. And as you've flown over that region, and commonly this is an aerial view. There's a lot of center pivot irrigation. You have a big municipal water well. You'll have one of those irrigation channels that are usually run on diesel engines and rotate around the pivot point. And what it'll do is it'll just kind of continuously move around and hydrate the field. So here's an example of it on wheels migrating around, with the system. And as a result, this High Plains Aquifer region actually covers about 174,000 square miles of area. It's a pretty flat line. It's all part of the plateau in this region. So you have the Rockies over here, and then you basically see this shallowly grading plateau down into the plains. Basically the history of the area is that this was settled in about 1800s. Settlers developed the land, but at the time, and you've sort of know this, you've heard about this in terms of the Dust Bowl and things like that. Farming was basically believed to be difficult and not particularly viable. In fact, the U.S. government at the time was trying to recruit people to go to the area by promising them parcels of land, chickens and goats. There's all different. I have to look up exactly what they gave out, but there was actually plans to provide people with livestock and rations and incentives to go to this area because farming was just believed to be not viable. Very modest rainfall, and the land was considered near unfit for agriculture and in that case for living. So most people were sort of range folks. They might have had some low use or low free ranging cattle or some goat farm or stuff like that. Things that didn't have a high amount of water requirements or high amount of vegetation requirements. Certainly farming wasn't really part of the question. It's really when the High Plains Aquifer, the Ogallala Aquifer specifically, was sort of discovered, if you will, where people became common to actually not do hand dug wells, but drilled wells with pumps. That this aquifer became really important. People started realizing, hey, there's plenty of sun here, there's plenty of warmth here, the soil's rich. If we have water, we have amazing agriculture. Of course, that's the history of the region. So the Ogallala is the actual geological formation that most of the High Plains Aquifer is in. This gives you a map of the thickness of that unit. You can see up here in Nebraska, it can be, well more than 1,000 foot thick. It thins out a bit as you get further to the south, but still can be in a few hundreds of feet thick. And 100-foot thick aquifer is a pretty serious aquifer. For perspective, the Ogallala contains about as much water as Lake Huron. So that's quite a big region. The bad news is we're going to get to, looks like probably in the next class, is that groundwater in this region, because of agricultural use, within the last probably 90 years almost entirely, is being used at about 20 times the rate of natural recharge. So as I noted before, a very modest amount of vegetation, a modest amount of precipitation. There is actually a modest vegetation, mostly low-lying grasslands in the area. And most of that is because this region of the Rockies actually creates a rain shadow. So the dominant precipitation patterns coming from west to east. Over the Rockies, most of the water, as the clouds move up the Rockies, there's adiabatic um, cooling, and precipitation often occurs on the west side of the Rockies. East side of the Rockies and down in the high plains is actually quite dry and sunny. In fact, on most years, Denver wins the sunniest city in the nation award, and most of this region here is actually quite sunny as well. Um, but groundwater being the only real viable source of water for agriculture or any other use, withdrawals from about 20 times rate of recharge. Most of the recharge that comes from occasional storms that move up into the high plains region from the Gulf Coast. So actually, hurricanes, tropical storms can bring some moisture into the region. Occasionally, when you have strong El Nino years, as we talked about, particularly as El Ninos are intensified, you see major rains in North and South Dakota, North and South Dakota is above the high plains aquifer, which can contribute some water. So, bottom line is there's not a great prospect for rainwater. So most of the water comes from snowfall melt in this Rockies, although most of the rainfall, most of the snowpack is on the west side of the Rockies, so it doesn't greatly influence it. So, for example, cities in this region, Lincoln, Nebraska, Lubbock, Texas, have large and increasing populations, and they have, truly critical, serious water shortage problems. In fact, these are some of the most well-monitored water wells, most well-monitored aquifer probably anywhere in the world, based on people really focusing and trying to do everything they can to manage the balance of this aquifer use in this region. But again, like the southwestern part of the U.S. here in Arizona, New Mexico, the problem is really compounded by extreme drought. It's really the rare perfect El Nino that provides rainwater, or a tropical storm. Other than that, most of the time it's a fairly dry area. So we're at 10 o'clock here. I'm gonna have to stop there. Give time if anyone has any questions, but otherwise we'll pick up with the Ogallala Aquifer discussion on Friday. Hope everyone has a good day.